Welcome back. This will be lecture 22. EC253C. Today we will be discussing about a very important concept in any microcontroller, that is timers. So we'll be discussing about AVR timers. Of course, their programming, AVR timer programming. In next few lectures, we will be discussing timers only. We will be discussing about need of timers, Also, we'll be discussing about different timers in ATmega 328. In the microcontroller we have been discussing so far ATmega 328, we'll be discussing what are the different timers present in ATmega 328 microcontroller. To effectively program timers, we need to study about the registers associated with these timers. Next we'll be discussing about the different registers associated with each of these timers. Registers associated, and then we are going to discuss about the different timer modes. What are the different modes there? What are the different modes they support at the timers in ATmega 328? So different timer modes. We'll be also discussing about how to program these timers in assembly language programming and C, of course, because now we have studied about C also. And finally we'll be also discussing about how these timers can be used as counters. Timers as counters to actually count the events happening outside the microcontroller. So these are the few topics we'll be discussing in this lecture, and maybe a couple of next lectures also. We'll be discussing about what's the need of timers, then different timers present in our ATmega 328 microcontroller, the registers and different timer modes, and how to program these timers and how to use these timers as counters. Let's start with need of timers. Need of timers. As you know, many applications in embedded systems, they need to generate exact time delays. So far we have been generating these time delays maybe using NOP operations, or executing NOP operation a number of times, or in high level language program we have some predefined functions, and those predefined functions actually use these NOP operations, executing these NOP operations. That's one way, but more accurate, better way of generating time delays is timers. For example, in a digital clock, we must know the exact amount of time between 2 seconds. When we have, for example, I have a digital clock and it displays time something like this: 09:36:43. This is the present time, for example, of a digital clock. So after every second it needs to increment. 43 needs to become 44, and similarly after every minute this number here needs to increment, and similarly after an hour this number needs to increment. So we need exact time delays. We need to generate exact time delays to run this embedded system, to run the digital clock smoothly. Also in some other embedded systems like maybe microwave ovens, we need to keep track of exact time delays, the exact time that has elapsed between two events. So there we use timers. Also, in many applications we need to count an event that is happening outside the microcontroller. For example, we have an embedded system and it needs to count the number of persons entering in a room. So we can use these timers as counters and count the events happening outside the microcontroller. So in these times we basically what exactly is a timer, what is inside a timer? We basically have a register that increments itself at a given rate. In case of timers, this rate is determined by the crystal frequency, crystal oscillator that is connected to the microcontroller. Or in case of counters, this register auto increments itself after occurrence of a particular event. So basically we might have a register and we call it a timer, and it's a counter register, it counts. Or let me write like this, it's a counter register. Counter register is a register, maybe 8 bits, maybe 16 bits. So let's assume it's an 8-bit register for now. And this register, it counts, it auto increments itself. Let's assume that we have loaded, or on reset it contains the value 00000000. That's 00 in hex, contains the value 00. Okay, so it increments itself at a given rate, and that rate is actually governed by the oscillator frequency connected, or this rate can also be can be governed by an external source, by an event happening outside the microcontroller. So there's an input that actually makes to tick this counter register. After a given time it will be 01. After again this, after the a time interval, it will be 02 until it will reach 0xff, that means 255 11111111. And there's an input. Whenever there is an input, it increments itself. So this input, it can come directly from the oscillator frequency, or it can be an event that's happening outside the microcontroller. If this input is controlled by the oscillator frequency, then we call it as a timer. And if this input is controlled by an external event, then we call it as a counter. For example, we might have something called as multiplexer here. There may be two inputs to this multiplexer, 2:1 multiplexer. One input is the oscillator frequency, and the second input may be some external source. If we want this counter register to increment itself at a given rate, and that rate is determined by the oscillator, we will select this input of the, we will actually transfer this input of the multiplexer to the output, counter timer. And if we want that this register should act as a counter to only increment itself when some particular event happens outside the microcontroller, then the external source input of this 2:1 multiplexer will be transferred to the output. And what happens once this counter reaches to the maximum number 0xff, when it auto increments after it, the value will again become 00, because if we add 1 to ff, we will get 100000000. But since this register is only 8 bits wide, so this 1 will be lost and we will have 0000. So the maximum counting capability of a counting register or a timer is determined by number of bits in that register. So what happens whenever it overflows from FF to 00, we might have a flag, a single bit memory, which is set. We call it overflow flag. And whenever our counter register overflows from FF to 00, this flag will be automatically set by the microcontroller, thus informing us that we have reached the maximum limit and we are starting again. Now, since the speed of the oscillator is known, we know the crystal frequency of this oscillator, we can calculate the tick period, that means the increment period of this register. And thus, from the contents of this register, we may know how much time has elapsed. For example, if the crystal frequency connected to the microcontroller is 1 megahertz, after a certain period of time we came to know that a number inside this counter register, we read the counter register and we came to know that the number is, for example, 0x09. That means 9 time periods have elapsed. One time period is equal to, since the frequency in 1 megahertz, one time period will be 1 microseconds. That means 9 microseconds have elapsed since the counter register was reset. So one way to generate a certain time delay is to clear the counter. We may clear the contents of the counter, that means load zeros in all the bits of the counter register and wait until counter reaches a certain number. Again, for example, the oscillator frequency is 1 megahertz. That means each tick period is equal to 1 microsecond. Each increment will take 1 microsecond. So if we need a delay of 100 microseconds, what we will do, we will clear contents of R and wait until R becomes equal to 100 in decimal, of course. And there's another way of actually generating the same time delay. That's to load this register R, this counter register, to load it with a specified number and wait until it overflows. For example, again, if the crystal frequency connected is 1 megahertz, that means each increment will take 1 microsecond, and now we need 100 microseconds delay. So we must start, when will it overflow? It will overflow at 255. So we must start with 255 minus 100. That means 155. So we can load this 155. The hexadecimal or the binary equivalent of here, it will be equal to 155 will be equal to 1, 2, 4, 8, 16, 32, 64, 128. It will be equal to 128. That means 27, 16, 11, 1, 3, 2, 1. So we will load this counter register with a value 1001, 10011. So after one increment, it will become, it is 1001, 1011. So after the increment, it will become equal to 1001, 1100, and then 1001, 1101, and finally it will be equal to 11111111. How much time it will take to become 111111 and subsequently overflow? It will take 100 ticks, and sorry, it will take 100 ticks. Yes, it will take 100 ticks, and since each tick is equal to 1 microseconds, so it will take 100 microseconds to overflow. And when it will overflow, the overflow flag will be set, and we will come to know that the desired time period has elapsed. So this is another way. So there are two ways: either we clear the contents of this counter register and keep a track when it has reached a desired value, or we calculate and store a specific value inside this counter register, and it keeps on incrementing until it overflows. The time between between storing a value and the overflow will give us the lapse, will give us our desired time period. We'll be discussing these things in more detail when we go in the details of the timers. This was just to give you an overview how a particular timer or how a timer works. So coming back to Atmega 328, what are the different timers in Atmega 328? In Atmega 328, in AVR microcontrollers, there are usually 1 to 6 timers. Some AVR microcontrollers have one timer and some have 6, some have 2, 3, 4 or 5, 1 to 6 timers, and it depends upon actually the particular family and the member. And those timers, we name them as timer 0, timer 1, timer 2, timer 3, timer 4 and timer 5. In case of Atmega 328, we have only 3 timers. We call them timer 0, 1 and 2. Some of these timers in Atmega 328 microcontroller, in fact most of these timers are 8-bit, but some are 16-bit also. So 8-bit timers can count from 0 to 255, but 16-bit timers can count from 0 to 2 raised power 4, 8, 16, 32, 61, 20, 56, 0.2, 2 raised power 16. That comes to 4, 8, 16, 32, 64,000 something. Okay, that's actually from 0 to F in hex. In case of Atmega 328, we have only 3 timers: timer 0, timer 1 and timer 2. Timer 0 is an 8-bit timer. It will count from 0 to 255 or 0 to FF. Timer 2 is also an 8-bit timer. That means the register, the counter register inside this timer is only 8 bits wide. But timer 1 is 16 bits. Before discussing these timers, how they work and the programs associated with them, let us discuss about the basic registers that are present, that are actually associated with each of these timers. So registers associated. I'll make a block. So now we have 3 timers. We have to discuss timer 0, timer 1 and timer 2. Usually, in fact, for all these timers, we have 6 registers. So there are 6 registers. Associated with each of these timers. What's the job of these 6 registers? First of all, we have a counter register that we call timer counter, and the short form is let me discuss the register with timer 0. Same will be case with timer 1 and timer 2. Only difference is some of the registers in timer 1 will be 60. Some of the registers in timer 1 will be 16 bits. So this is for timer 0 only. Timer 0. So first of the most important register is the counter register, in which we count the numbers, which auto increments at a given rate, and that's register in a timer counters T, C and T. TCNT, and for timer 0 we call it TCNT0. This will be present also in timer, and in timer 0 it will be 8 bits, but in timer 1 it will be 16 bits. TCNT0. In case of timer 1 it will be TCNT1, and in case of timer 2 it will be TCNT2. So the first register that's present inside or that is actually associated with each timer is the timer counter register, TCNTN. It will be 0, 1, 2, or for some other microcontroller it can be up to 5 also. TCNT. This register is used to actually count. This is the register that auto increments. And when this register reaches to a maximum value and then overflows, you should remember it doesn't set the flag when it reaches the maximum value. It sets the flag when it overflows from FF to 00. It sets a flag, and that flag is known as timer overflow flag. So this is a single memory bit, TOV. In case of timer 0, it's known as TOV0. This is the first register. Okay, then in case of Atmega 328 microcontrollers, we have an output compare register. We call it, in fact we have two output compare registers. So those registers are known as output compare registers. We have two output compare registers, OCR output compare register. Since they are for timer 0, so OCR0, and since we have two of them, we call them OCR0A and OCR0B. Output compare register A and output compare register B. What's the job of these output compare register? Sometimes we don't need our timers to reach the maximum limit FF. We want them to stop at a particular number. Maybe we only want to count them from 00 up to 0E, or from 00 to 38. So that number is loaded in one of these registers. For example, if I want my timer to count from 00 up to 43, so what I will do, I will load this 43 in one of these output compare registers, and what my timer will do, after every tick it will compare its contents with these output compare registers, and if it has reached the value that is present inside these output compare registers, it will set a particular flag. Same wise it used to set the flag when it likewise when it used to set the overflow flag when it overflowed from FF to 00. So for example, there will be a particular number in output compare register A, output compare, and also in output compare register B. So after every tick, my timer will compare the contents of TCNT0 with OCR0A and with OCR0B. So actually there will be a comparator block that will check whether the contents are equal. This compare block will have two inputs, and there will be another comparator block. This also will have two inputs, but again it has to check the contents, compare the contents of counter register with OCR0B register. OCRB0 has I have loaded it with a particular number before starting the timer, and if whenever the contents of timer counter register becomes equal to either OCR0A and OCR0B, a particular flag is set. In case of OCR0A, that flag is known as, it is again a single bit memory, OCF0A, and for if the contents of timer counter become equal to OCR0B, there is another flag, that's OCF0B. So you may be seeing that there are actually different modes in which I can run my timer. There's a mode where I run it as a timer, or whether I run it as counter. Again, there are different modes inside that timer itself. I can use it to reach the maximum value and set this flag, or I can simply put some other value in these compare registers and stop my timer, in fact reload my timer with 00 when it reaches to that particular number. So these are different modes of a timer, and all of them have their own advantages. So to determine in which mode a particular timer runs, we have two control registers. We call them timer control registers, and they are associated with each timer. With timer 0 we have two control registers. With timer 1 we again will be having two control registers, and same is with timer 2. And those control registers, again they are 8-bit wide. We call them TCC, timer control register, for timer 0, TCCR0A, and there is another control register, TCCR0 or 0B. So these are 5 basic registers present inside every timer. So we had counter register, we have two output compare registers, 2, 3, and then we have two control registers which actually control the functioning of timer, in which mode we have to use the timers. And then the 6th register is actually these flags, because flags are also part of a register. We have a flag register, we call it timer flag register 0 for timer 0. This is again an 8-bit register. The first 5 bits are unused, we don't use them because we have only 3 flags, and those 3, the 0th bit will be timer overflow flag. I have shown it here also. And then we have OCF0A and OCF0B. So again we have 6 registers. We have timer counter register that's used to count, and then we have OCR0A and now I am making this more general. We will be having OCRNA and OCRNB, where N denotes the particular timer 0, timer 1, or timer 2, and these are output compare registers. Output compare registers. Similarly, we have control registers, 2, and this was 3, this is 4. 4 will be TC, timer control register, TCCRNA, and TCCRNB. Again we call them timer control registers. These are used to actually start the timer, to set a timer mode and other things, and also to decide whether to use the timer as a timer or as a counter. So basically, before starting a timer, we need to know in which mode we need to run this timer, and then load a particular value in these timers, in these registers, in the TCCRNA and TCCRNB, and again denotes the timer, which timer 0, 1, or 2. And after loading timer controller with a particular value, then we need to know how much time delay we need, and accordingly we will load this timer count register, or we will load OCCRNA and OCCRNB. Sorry, this was OCC. or OC. OC, yes. And then there is the sixth register, that's known as timer flag register, which contains the three flags. That's T, I, F, R, N. This is the flag register. Again, timer control registers are used for setting modes of the operation. For example, to specify if a timer works as a timer or a counter, or whether we use OCR0A or OCR0B, or we wait for overflow. Also, these timer control registers are used to actually set the speed of the timers. I told you that the speed with which the timer increments depends upon the crystal frequency, but sometimes we can alter the speed. We can tell the timer to actually increment at half this rate of the crystal frequency, or 1/4 of the rate of the crystal frequency. That we do by actually loading a particular value in these timer control registers. One thing you should note, these registers that are associated with each of these timers. Now 6 registers associated with timer 0, we have 18 registers with timer 0, 1 and 2 combined. These are part of input output register memory. We have discussed the RAM of Atmega 328, where there was a section of input output register memory. Our registers associated with ports are part of this input output register memory, and also the registers associated with these timers are part of this input output register memory. Since they are part of input output register memory, we can use instructions in and out with them, because you must remember that the instructions in and out, in for reading the data of a particular register and out for writing the data to a particular register, can only be used for only those registers which are part of input output register memory. So basically, if I need to put a particular value in any of these registers, maybe TC and T0, I need to put a value, for example 25. So I can basically write LDI 20 25, then I will out this value, out TC and T0 20. So my timer counter register of timer 0 will get value 25, and if I need to read a value, I will use the instruction in, which we have already discussed. So the next thing we will be discussing how these two registers, TCCRNA and TCCRNB, are used to actually set the timer modes, or what are the different timer modes. So that will be in next video, inshallah. That's it. Thank you.